So hello and a very warm welcome to all of you. And I would like to mention that this session is being recorded. Sorry. There's still people joining in. Sorry. Yeah. So to give you a quick introduction, I'm Sonia Rao and I'll be moderating this webinar today. I have been part of Compular for more than 2 years and I have a PhD in computational chemistry. So let me start with giving you a short introduction about Compular. We are a spin-out company from Chalmers University of Technology, and our aim is to digitalize materials development. The purpose of today's webinar is to share how molecular scale modeling can provide the parameters needed for high-quality cell modeling. So let me introduce our speakers for today's session. We have Rasmus Andersen, founder and CEO of Compular. Rasmus has a PhD in physics from Professor Patrick Johansson's group at Chalmers, and he'll be joined by Magnus Ram, CTO of Compular, and he also has a PhD in physics from Chalmers. We're also very excited to introduce our featured speaker, Elisabeth Ierbe from CD Tech Energy Storage, who's a team leader there. And she'll share her insights from a project between Compular and CD Tech on simulating sodium-ion batteries. Please feel free to write down your questions on chat, and you can also ask them in our Q&A sessions. So without much delay, I would invite Magnus to now start the session. Yeah.
Yes, thank you very much, Sonia, and I'm happy to see a lot of people in the room. You never know when you invite things like this, whether there will be people or not, so it's good to see a lot of people joining. So we're going to talk today a lot about battery models. And with battery models, what do we mean by that? So today we're going to essentially mean that we're modeling the behavior of a battery cell. And the battery cell, as you probably know, it's actually a very complicated thing with you have an anode and a cathode, and you have a separator, and you have electrolyte, and all of these parts all have a certain microstructure and so on. So this is something that you can model in 3 dimensions, if you like, plus time, of course, and see what happens. But those kinds of models, they tend to become quite expensive. So what people usually do is that they squash the battery, so to say, in 2 dimensions. They average over the y and z directions, if you like, and you're left with just one coordinate x here that sort of takes you from the anode over the separator to the cathode. So that makes it a lot simpler, but you cannot make it too simple. You still need to take into account that you have these particles with active material, and so that the way to incorporate that into the model is that you can call these you can approximate these as spherical particles, and so that gives you the second dimension. So you have x and you have r, so that's kind of pseudo 2-dimensional. So this is usually called P2D model or Doyle-Fuller-Newman models, and so that is something that we will bring up a lot today. Now, a challenge with these models is that in order to even run them, you need a lot of input parameters. You need some parameters that describe the materials in your system. So I've noted down a bunch of them here. This is by no means all of them, but it's sort of a selection of typical parameters that you need to know in order to do these simulations. So some of them are quite geometrical in nature, describing the geometry, so to say, of your system or the microstructure. So the particle surface area per volume, for example, and the porosity of the system. Some are more kinetics related. It's the reaction rate for how fast does your ions enter and leave the active material, for example. And then it's also the open circuit potential, which is more of a thermodynamic property that describes how the voltage of the system varies with ion loading in the active material. And then it's transport properties, conductivity in active material and in electrolyte, and it's also diffusivity, and it's transference number, and it's something called the thermodynamic factor. And all of these are important parameters that you sort of need to know in order to run the model. So how do you know it? Well, on a good day, you will be able to have a database where you can find the material parameters. So the problem, though, is that very often there will be no database like that. So in the battery field, it's generally quite hard to find comprehensive databases with a lot of different materials and so on. And especially if you're working on a completely new battery chemistry, there will, of course, not be anything like that because no one has measured it. So what can you do then? Well, of course, you can measure them yourself. For some properties that will work perfectly well, but for others it will be very tricky. You might not have the equipment, it can be time consuming, it can be expensive, and even if you try to do it, the results might not be very reliable because it's just inherently very difficult to access some of these parameters. So what most people end up doing in the end is that to some extent you just accept that you don't know all of them. And instead you guess the parameters, and then you run a model, you get some results, and then you see that, well, it didn't really match what I see in experiments, so then you tweak the input parameters and you run again, and you sort of iterate that process until you get the result that you expect. So obviously there is some limitations in the predictive power of such an approach, and there's always a risk there that you will get the right result for the wrong reason, so to say, that you don't describe the physics as it actually is. So what we're proposing, and what we will show some examples of today, is that you can also use a physics-based approach to this, that you can actually simulate the materials with other kinds of simulations that start rather more from first principles, so to say. So this is what we're doing a lot at Compular, and the properties that we will show you examples of today are these 4 properties written in orange here, which together they make a full description of ion transport in the electrolyte. So what approach are we actually taking here? So what we're using is something called molecular dynamics. I would expect that most of you probably know at least a little bit about it, but just to give you a very brief intro to it, it's in its core, it's a very simple model. It's essentially that you have all your atoms in a box, and then you have a model that describes what the force between these atoms are, depending on where they are located with respect to each other. And so then you have Newtonian mechanics, and you can just propagate the system forward in time. So what this means, and what we're doing then, is that we have a model that with which we can simulate the microscopic movement of atoms, and then we can use statistical mechanics to extract the material properties, the macroscopic material properties that we're interested in. And so the contribution from Rasmus' PhD was actually in this middle step here, where we analyze the simulations. So we have a code, in-house code that we use for this, that where we do some well-grounded approximations that in the end mean that we don't need as much data as would usually be needed to extract many of these transport properties. So it makes a very efficient job of extracting as much knowledge as possible from a short simulation as possible, and that means it is cheaper than it otherwise would have been, so that's very important. So to give you some feeling for what this might look like, so here's a movie from a simulation. So what you get out is essentially just the atoms moving around in a box. But then with our code, we identify which atoms are actually bonded together and which are not. And then from that, we can also see which molecules and ions stick together in the simulation. So this is an example here of where we have a lithium ion in the middle, and it is surrounded by a couple of different solvent molecules. So this is an ion with its subation shell. And this is information that we then use to actually compute some transport properties. I'm not going to go into detail of exactly how that is done. Some of it is in the papers that you can read. But what you need to know is that from these simulations we can compute transport properties. So then you could ask, does it work? And of course we have done a lot of benchmarking of this. And here you see an example of that. This is from a white paper that we published quite recently. So what we did there was that we took 3 different electrolytes, or actually 3 different solvents, and then we added lithium PF6 to that with different amounts. So on the x-axis you have the concentration of salt. And so here is an example from 20 degrees Celsius. And then in those simulations we computed these 4 different transport properties. And so here at the top you have ionic conductivity, and at the bottom you have salt diffusivity. And overall I would say that it compares quite well. It's not perfect. You should never expect perfect match between simulation and experiment. But overall it does a good job. You can argue, or you can see at low concentrations we tend to do a slightly worse job than at higher concentration, and that's because we have in those simulations the concentration of salt is so low, so there will be very few ions actually in the simulation, and that gives us worse statistics, and then it's a bit harder to make a good prediction. Now, you could argue that ionic conductivity and salt diffusivity, it's actually not that hard to measure. So if you have that equipment, and if you have mixed these electrolytes, you might be better off actually just measuring them. But if you don't want to buy the chemicals and mix them, you could still be better off just running the simulations. But there are other properties that are harder to measure in experiments. So here we're looking at the same system, but now at transference number at the top and thermodynamic factor at the bottom. And you can almost see from the experimental lines, I forgot to say that, but the blue lines are experimental lines from a paper from 2019 that is often considered state-of-the-art for measuring these properties. Oranges are simulations, and you can almost see from the blue lines that this is hard to measure experimentally because the error bars are high. The lines are not particularly smooth. They vary in a way that you wouldn't really expect, and also if you look at the absolute scale here, so to say, at transference number, they see a lot of negative transference numbers, which is not impossible physically, but it's also not particularly probable, I would say, that this should happen in this system. You can argue about that, of course, but it is a bit suspicious. On the other hand, the simulated results are pretty smooth and with more or less the expected values, so to say, around 0.4 for the transference number. And there's a similar story for the thermodynamic factor, that we get very smooth lines. So in this case, I would rather want to ask the opposite question, so to say, is do actually experiments match MD predictions here? Because I would argue that in a way the simulations can actually be a bit more reliable in this case. So this is really kind of a multi-scale modeling approach we will show here today, where we're taking results from simulations on a very small time and length scale, where you can't really predict the actual behavior of a battery, but then we can feed that result into another model where you can actually access these time and length scales that are relevant for batteries. So as a first example of this, I will hand over to Eli, who will talk a bit about sodium-ion batteries, I believe.
Shall I start?
Yeah, please go ahead and share your screen.
Okay, so yes, I will start sharing my presentation. Okay, let me. Can you see my slides?
Yeah.
And can you see me as well?
Yes, we can.
Okay, so first of all, thank you very much for the invitation. It's a pleasure to be here and explain the work that we have done together with Compular with the sodium-ion technology, in particular to to using this weak coupling approach, where molecular dynamics has been used for estimating transport properties of the electrolyte, and this information has been somehow embedded into the cell modeling, and where we were able to see and capture the influence on these specific properties. So let me start saying that I'm team leader at Cidetec Energy Storage, which is a non-profit private organization in San Sebastian, and we have released, we have activities in the modeling where we are somehow sharing customized models to clients and industry, but also software as a service platform where we have embedded certain models that we have developed in-house. So yeah, I will also share later now. Just an example is that we've been working a lot in the continuous scale, where we can capture obviously voltage profiles depending on certain properties of the electrodes, but you are somehow homogenizing properties there, and then it's quite important also to include information from the electrolyte, but then we have also go into the deeper understanding on the multi-scale approach, where we have also developed mesoscale modeling, where we can capture microstructure and particle level modeling. And something that we have done also is embed artificial intelligence, where we've been dedicated a lot of effort for predicting the lifetime and also safety scenarios. Yeah, and this is the information on the web page application I was talking about in the beginning, called Proteo. So just as a brief introduction of our capabilities. But now I wanted to emphasize on the main purpose of having me in this webinar is to show our work together with Compular, where we were able to somehow connect the specific simulation performed at Compular through the molecular dynamics, where they are estimating certain properties of the electrolyte, and including this information into the P2D approach, where we can predict the cell properties. And we normally use this approach just for optimization purposes, where we normally extract something like a wagon plot, depending on certain electrode properties. And this is something that we've been dedicated a lot of effort parameterizing electrodes. But obviously, in this case, we are talking about the electrolyte, where we obviously need to have information on these transport properties. And it's true that on the experimental side, we've been dedicated a lot of effort extracting the transport properties through these experiments. And I can assure you that it takes a lot of time assembling. I mean, if you are performing at least electrochemical tests to extract, for instance, electrolyte diffusion coefficient, it takes a lot of time, because you need to assemble a lot of symmetrical cells, build also the electrolyte with different salt concentration. If you want to capture this information into the properties, transport properties, or if at least if you want to consider temperature issues into the properties. So this is somehow is quite time consuming, where simulations can somehow save a lot of time. And this is one example in which we were focusing today, and in particular to the sodium ion, because it's quite novel, and we've been addressing a lot of issues with the sodium ion, and also because we are also involved in a project in which we were validating our model against specific electrodes, and we wanted to make those trial. So here is a QR code that links to the white paper that we wrote together with Compular, Cidetec and Compular together. And if anyone is interested, could just take a picture of it. So main purpose is to get extracted through the molecular dynamics these transport properties. And the good thing of having this molecular dynamic is that you can compute these properties depending on, for instance, different salt concentration, and then you can easily include this information into the continuous scale models and see the influence and impact. So this is what we have been working on. And for that, we have selected 2 electrolytes that are somehow listed here. And through the Compular tool, molecular dynamics, that Magnus already explained, the physics behind. We were able to get information on the ionic conductivity, diffusion coefficient, thermodynamic factor, and then the transfer number. And the good thing is that we were able to have in these ranges with very low concentration on the, in this case, sodium salt, and high concentrated sodium salt. So 2 electrolytes that were selected, that in this case we changed the solvents, but also one additive that was missing in here, and then we vary, as I was mentioning, the salt concentration in the sodium PFS6. Okay, and here you can see the difference between these properties, and we wanted to see this, how much is impacting on the cell performance. And the first thing we did is that sometimes what we usually do in the experiments is to try to minimize the number of experiments, and for that sometimes we assume that these properties are constant during any kind of concentration ranges. So first thing we did is to assume that we had a constant concentration all along the cell, and then we compare the results with these properties that were including these variants in the concentration, and this is the results. So this is the typical Ragon plot that we usually get, where we can compute through the Proteo energy versus the power, and then we normally vary different kind of properties. And for instance, typical things that we usually do is to change the C rate, which obviously is very interesting because normally at high C rate, you might be very far from the theoretical energy density, and obviously this is something to be considered depending on the end user needs or KPIs that needs to be achieved. And then something that we normally do is to play with certain parameters. And in this case, we were playing with the thickness parameters of both the anode and cathode. So this is the starting point in red. This is the thickness of the anode, while this is for the cathode, while we multiply by 3 and 1.7, just to explore what happens with the high loading. And in this case, what we are comparing is the type B, which is basically this EC, PC, and MC based electrolyte with a constant value of concentration, or including this influence on the concentration into the transport properties. And what we see obviously is that certain deviation, and seeing clearly how important it is to achieve or to extract these parameters accurately, describing all the dependencies. And in this case, we were only considering the concentration, but all the relevant parameters should be considered in advance. So basically, this is just to show how important is to accurately do the parameterization. And obviously, this modeling can support a lot on that because it's saving the time on the experiments. So, and the next thing what we are doing is basically compare this type A and type B, which are the 2 electrolytes that were used in this specific study based on our sodium ion technology. That was, as I was mentioning before, validated previously in advance with our own electrodes at CDTEC. So here we are comparing, as I was saying, the electrolyte A and electrolyte B, and again, what we play is with the thicknesses, but obviously this can be, we can play with many parameters as the P to D might consider, like for instance, the porosity, tortuosity, or any other parameters that is included in the model. So here, what we see is obviously, again, depending on the C rate, we are seeing that the differences between the circle and the square is completely, it gets higher. And in the end, what we are seeing that in this particular case, we are able to obviously plot the voltage profile, complete voltage profile. And in this case, we are considering the discharge is that, for instance, a high C rate, but very, like, let's say that it's medium thickness electrode, there is not so much difference between the type A and type B electrolyte. So this is one example, and this is one study in which obviously it's really important to have these kind of tools in which you can connect electrolyte properties and cell performance. And the other example I wanted to emphasize is that in this case, we are focusing in the high thickness or high loading electrodes. Obviously, the difference between these two, between the square and the circle, it's much bigger if we compare to the previous one. And this is because obviously in the high loading electrodes, you might have like much more transport limitation. So, and here it's if we see directly the voltage profiles, the difference is quite obvious. So very quickly maybe, but we wanted to show this exercise in which we were collaborating with Compular, because we see a lot of complementarities between these molecular dynamics and the continuous scale models, where we can, this was a very straightforward exercise that can be somehow extended to many other aspects and approaches, and we will be working in the future as well. So basically, to sum up, is that in this case, we were just showing this sample in which the Compular is computing these transport properties of the electrolyte for this specific sodium-ion technology, and this has been embedded in the Proteo tool, just to evaluate that how important is the first slide is the parameterization of the electrolyte, to do the parameterization accurately, but then we could say through this molecular dynamics efficiently, and see the impact on these differences between the composition at the cell level. And then obviously, as this is continuous scale, we can play with many parameters as the model includes. Like for instance, in this case, we were showing the impact on the loading of thicknesses, but we can play with the other parameters as I was mentioning, so like the tortuosity or porosity, because these are very, very common parameters that we normally, when we are manufacturing electrodes, these are also considered in the manufacturing and in the whole value chain. So, and these kind of tools is like becomes like crucial in order to do this cell design and optimization, because you can know in advance how important can be to have one composition of the electrolyte or the others, or if there is a chance to optimize the specific properties of the electrolyte. So yeah, with this, I would like to end, and thank you again for giving me the opportunity to be here. And I hope I more or less describe properly the work we have done together with Compular. Thank you very much.
Thanks a lot, Eli. And if there are any questions, I would please ask you all to go ahead, raise your hand, or just ask directly, or you can even put it up in the chat. So we have one question from Arun, and the question is, for MD simulations, which force fields are being used?
Yes, so for what we're showing today, it's the Apple MP force field. So if you don't know it, it's a polarized force field that is generally considered, I would say, the best for lithium-ion and sodium-ion electrolytes.
Are there any other questions? Well, if not, then let's just move on to our next speaker, and I'll ask Rasmus to start his presentation.
Yes, so thank you. So we're moving on now to still P2D modeling, but in the context of cell aging. So what I'm presenting here is another project that we did together with COMSOL, who unfortunately couldn't join today. And the purpose is to study how aging affects the electrolyte properties, and then again how that affects the overall cell behavior. So in this study we used a simplified reaction model wherein EC is reacting to form an SEI layer in the presence of lithium. So we have irreversible reaction rate, which is proportional to the lithium concentration, the EC concentration, and the overpotential at the graphite electrode. And when we do so, we conserve volume, so the EC gets converted to the same volume of SCI. And what happens then is that we lower the electrolyte volume fraction. And this in turn then means that we get lower porosity and lower effective transport properties. So that's one effect. But what we also do here is that as we consume EC, we will get a different composition, a different solvent mixture. And this directly affects the intrinsic transport properties of the electrolyte, which is also something that we can capture by MD simulation. And this is the kind of thing that even if you do something ambitious like looking at aging in a P2D model, you wouldn't normally capture the effect on the electrolyte rheology. So first I will show you there what we got from the MD. Oh, sorry. What do I do? Yeah, okay.
Just don't push the to the
Yeah. So yeah, we first got the diffusivity to the left in this picture, and we see the expected shape that we get nonlinear but smooth decrease as we increase the salt concentration, and the different curves instead express the fraction of solvent that is EC. So we start from 30% EC and 70% EMC. And then we go down towards 0% EC when we've used it all up in the formation process. And what we see for the diffusivity is that if we remove the EC, we get an increase in diffusivity because EC is more viscous than EMC. If we're looking instead at the electrolyte conductivity, we see something which behaves a little bit different. So first, if we're looking at the concentration dependence for the salt concentration, we get the familiar shape. But if we're looking at varying EC content, we see that as we use up EC, we actually get lower conductivity, as opposed to what you would expect based on the diffusivity results. And the reason for this is that EC is a more powerful solvent of the lithium salt than EMC is. So it's better at separating the ions, and then the effective charge concentration becomes higher with more EC. With respect to when we vary, or with respect to...
Hello?
Sorry?
Can I interrupt you? Sorry to interrupt you. Can I ask you a question?
Okay, let's do one question, but we will later prefer to use them between the parts. But yes.
Okay, then probably end of the presentation we'll discuss. No worries.
Yes. Thank you. So if we're looking at the conductivity curve, we see that we also get, with decreasing amounts of EC, we get a shift to the right and a flattened profile for the conductivity. Looking at the thermodynamic factor, that is very close to linear for the salt concentration, and it doesn't depend a lot at all on the solvent composition. And finally, the transference number for lithium is around 0.31, independent of both salt concentration and solvent mixture. So then we move on to the cycling program that we used here. So we charge at 1C up to 4.3 volts cell voltage. So this is for an NMC cell. And then we hold there until the current is lower than the equivalent of C over 20. And then we discharge once again at 1C down to 3.1 voltage, 3.1 volt cell voltage. And then we repeat this until we reach 90% state of health. So then we come to the results. So if we're starting from the picture based on the electrolyte properties, and then we're going towards the consequences for cell operation. So the first thing that we see is that the higher diffusivity that we get with lower EC, when we take that effect into account, leads to a flatter salt concentration profile than we would get if we disregard this effect. So this is something which has a lot of repercussions in terms of the cell aging. And one way that we can see that is if we look at the end of the discharge cycle, we see that the polarization or the overpotential is way less when we take this changing electrolyte properties into account. So the blue one here is the reference where we have 100% state of health, and then the green is at 90% state of health when we take the changing electrolyte properties into account, whereas the red one is when we don't. And the upshot of this is that when we look at the lifetime of the cell, the predicted lifetime differs by 25%. So we'll see that if we do include these effects of changing electrolyte composition, then we predict a 25% longer lifetime for this particular cell, which obviously is quite important if you're doing cell design. So this is what we did together with COMSOL, and there is of course always future work to be done. We have a very good start with what we did both with CDTech and with COMSOL, but there are things which we don't cover yet. So one caveat to this COMSOL study is that we couldn't do as fast charge and discharge as we had originally intended. The differences between taking into account the changing rheology and not doing it is biggest if we do fast charge and discharge. And what we found here was that we got so big concentration gradients that we went outside of the sampled concentration range, and then we have to limit that a bit. So one thing which we would like to add is to predict the solubility limits, and then we can sample the whole range and also predict when you would start to get crystals forming. Then another thing which is very natural to add on is to look at the effect of temperature. So everything we've done or presented so far is at one constant temperature, but obviously, especially if you're doing fast charging and discharging, you would get local heat evolution, like you would get overall heat evolution, and it would also have a local dependence. So there we could, for each point in time and each coordinate across the cell, we could have different temperatures and then say how that changes the electrolyte properties. And this is something that we have ongoing in a project which will be a paper eventually. Another thing is that we just assumed one reaction mechanism and a quite simplified one. So obviously, if we can combine this with predicted reaction mechanisms and more flexible, then we can do this for more general cell chemistries, and we can involve other effects of side reactions and so on. And the final thing is that we're including here solvent mixture, and we're doing this in a lumped fashion, which is, I would say, it's what most people do, but then we could do it in a more explicitly multi-component transport theory framework. So what we're doing here is often good enough, but it's not actually exact. So that is something that we also are working on, including in the future. So yeah, so there will be questions very soon, but I would just like to take the chance to introduce a little bit more who we are in Compular. So we're a startup based in Gothenburg, Sweden, and what you see in the middle picture there is the whole team. So we're 10 people right now. And we're building molecular scale modeling suite, which is targeted for experimentalists. It could be for computationalists as well, but what we've seen is that the market of people who should use this in industrial materials development is not served, because most of the people who could have use of it don't have the computational expertise needed to use current tools. So we're making it really simple, and I'm going to leave over for Magnus eventually to show you a bit more on that. But we were founded in 2020, and we started out very narrowly focused on electrolyte development. But we're now at the point where we're looking into up and down the value chain. So for example, for cell design and the kind of things we talk about today. But we're also looking to broaden our scope to other areas. So if you have ideas for where you would like to apply these kind of simulation tools, do let us know. And
so thanks, Rasmus. And with that, I would ask anyone who has questions to please either write it on chat, or you can just unmute yourself and ask directly.
So let's maybe start with Nilesh, who's been waiting for a while.
Yeah, Nilesh, yes.
Thank you for giving me the opportunity. So first thing I would like to ask, your model is probably really good for the lithium ion, but Will it work for the lithium metal batteries? Because we are the user of the COMSOL, but in COMSOL still they don't have a degradation mechanism of the lithium metal. And second question is, we are very much familiar in case of lithium ion and EC-EMC combination that which ion make a combination with lithium during transport. But how exactly, if you have a different electrolyte, different anions, then what should be the molecular MD simulation, or what should be the criteria to select that correct ion pairing with the lithium in case of different combination?
So the first question was with regards to lithium metal cells as opposed to lithium ion cells. And there, like, depending on what you change, you need to change either how the electrolyte itself is modeled using MD, or you need to change how the cell model works. So I would expect that for, like, if you're going to do lithium metal, like you might want to have like a dendrite formation module. And I mean, there's no intercalation, so it's a little bit different there. I think most of those differences would mean that you would make different choices in COMSOL, and I'm not knowledgeable enough to know like how well supported that is right now. It could also be that you would need other parameters, and then most likely there are some of them that we could help you with as well. Maybe we would need to build something we don't have. And there are probably ones where you actually need to do some kind of experiment, or you do need to do like a global optimization of the parameters. But I can't go a lot into details there because we haven't done it and don't know in detail. So your other question was with regards to if we're changing the electrolyte composition. Is that correct?
Correct.
Yeah. So then we would use the same force field, and we would just simulate that other composition. We would vary in terms of concentration, solvent composition if we have consumption of one of the solvents, or if we vary temperature. And everything would be done in the same way from the MD point of view. Does that answer your questions?
Okay. First question, I think more or less we can discuss further offline. Yeah. That's true. I haven't attended the section of the molecular dynamics. I joined late, so I don't have a much idea about what exactly presented. Okay. But yes, we can still in this topic also we can discuss further offline or in a separate meeting.
We will make the recording available after the event, so you can look at what we presented there. And yes, we're happy to get in touch after it.
Hi, okay. I have a continuation with Nidesh question. This is regarding to the molecular dynamic simulation, where you are using different electrolyte composition. For that, for example, if I use other molecules, whichever is new, so you already have the built-in force fields, or you are developing it, or you are taking from somewhere else?
So yeah, as Magnus mentioned, we're mostly using FLMP right now, and it's pretty well supported. But if you're doing something really exotic, then we need to do some parameterization on the force field level as well. But we're happy to do that, depending on how exotic and how chemically complex it is. That might take different amounts of time.
Yeah, thank you.
Are there any further questions for Rasmus? Well, if not, then let's move on. And for this part of the session, I'll invite Magnus to actually give you all a preview or a short demo of how the Compular app actually works.
Yes, there we go. So, okay, yes. So what do we actually build here? So as Rasmus said, we're trying to make a tool that can be used by basically anyone who works somehow related to chemistry or physics. You don't need to be a computational expert. And so the first thing you might notice is that I run it in the browser. You just go to compularlab.com in order to start it. So the threshold to enter is really low. And we're building a bunch of different modules. A module is essentially one kind of simulation that will tell you something about something. And there is not a whole lot of them because we're really trying to. We're not building a general purpose molecular scale simulation tool here, but we're really building the kind of modules that we know will be useful for practitioners in this case in battery cells, but it can be other things as well. So I want to take the opportunity here to show just for these studies that we have shown you now, what would you do in Compular Lab to make that possible. So you would then use the molecular dynamics module. And in order to start a molecular dynamics simulation, I will just very briefly show you how that would be done. So you give it a name, let's call it webinar test. And then you specify what salt you're using, and then you already see now that this is not a general purpose MD tool, but it's really targeted to electrolytes because we expect you to have a salt here. So let's do lithium PF6. You can add additives, of course, if you want, but let's skip that and go straight for the solvent. And let's then do DE, why not DEC? 1 weight part and maybe 2 weight parts of EC. So there we go. There we have specified the full composition of the electrolyte. Then you can specify what conditions you want to run this under, temperature and pressure, and then there are just a few settings that you can toggle. Like if you're not interested in transport properties, for example, you can toggle that off and it will be a little bit cheaper. And then if we continue here, you will see what we are going to run under the hood here. So how many molecules will we use of each species here? And what does that mean in terms of concentrations and so on? So this is basically it. If I were to click submit job here, what would happen is that we would send this information to the cloud and we would run a simulation there. So that also means that you don't need HPC hardware or anything like that. That is sort of included when you sign up for Compular Lab. But I will not start the simulation now. I will rather, like any good TV chef, I have already prepared some results here. So anyway, what would happen if I started it is that you would see that this is in progress, and then in about 1 to 2 days roughly for these kinds of simulations, the results would be available here. And so here I have just added a little bit of example data. So this is a bunch of simulations that are related to the plots I showed you in the first part of the webinar where we had this benchmark data. But let's just look at something to see how it looks. So you can once again see what you put in to make sure that you're running what you think you're running. And then at the top we show you like what we believe is usually the most relevant results here. So in particular you see these 4 properties, transport properties that together specify the electrolyte completely in terms of the ion transport. So you can of course download this and put it into your P2D model, for example. And then you can go into a lot of detail. You can see like self-diffusivities, for example, for the different components of the electrolyte and a lot of different other properties. You can see things like radial distribution functions if you're curious about that. And you can, one thing we also do is that if you really want to go deep into this, we also show these dynamic species that I mentioned in the beginning, basically what molecules hang together in the simulation. So for example, here you can see that the most common solvation shell, it seems, for the lithium ion seems to be this one, where you have a lithium ion surrounded by 3 EC and 1 DMC. So if you really want to understand what goes on, you can look at this, and we also extract properties for these dynamic species. For example, what is the diffusivity of this one? And of course, usually you would want to compare different systems. So let's take these this same system that I showed in the beginning there with the different salt concentrations, but the same temperature and everything else. So here you can see like different properties for these, and then best thing here is that you can plot, you can make like custom plots here. So ionic connectivity as a function of lithium concentration would make sense. So here you get kind of the same plot as you saw in the beginning. So this is also under development, so there will be a lot more here as we learn what customers need. So we're running out of time a little bit, but let's just... I also want to do some marketing here, of course, since we have you all here. So you can also compute redox potentials. So this is not really related to what we have been talking about so far, but this is really a tool that makes it super easy to compute reduction potential and oxidation potential for molecules. You also get HOMO-LUMO values. So this can be useful for example, screening additives. If you want to have an additive that should degrade at the cathode interface at a particular voltage or something like that. We're also building a tool that we call molecular interactions, which is a tool for seeing what happens when you bring two molecules or an ion and a molecule close to each other. So this is also very much under development, but so in this case we have taken a lithium ion and a DEC molecule and we bring them close together and we see how the HOMO-LUMO value vary. So this will tell you something about how one can stabilize the other, for example, in terms of electrochemistry. So that was a very brief intro to our Compular Lab, but we're of course very happy to talk more about this with anyone who's interested, so feel free to get in touch with us. You can email us and you can of course also visit our website, either where we tell you who we are or Compular Lab where the tool is. And if you're really interested, you can sign up there for a demo account where you will be able to click around in the app and so on. But you will not be able to start any simulations. For that you need to get in touch with us first.
Well, thanks, Magnus. There's a question by Muwafa Khatib. Like, you can ask it yourself if you want to.
Oh yeah, I saw the.
Yeah. Or I can read it out in case you. Yeah. So okay, I'll read out the question. So the question is: are you optimistic that sometime soon there would be a general force field for dynamic properties of electrolyte? Maybe a model that is based on dipole moment of solvent component. For example, ZBL potential describes ion-solid intercations or I think interactions here. Yeah. Okay. So ZBL potential describes ion-solid interactions for all elements with relatively good accuracy.
I'm not familiar with ZBL there.
Yeah.
But overall, I think having a sort of a force field that would catch everything is. I'm not very optimistic about that. Overall, electrolytes are difficult because of all the point charges you have there and so on. So it is very tricky, and that has been seen also when people do neural network potentials, that it is actually very hard to get them to work, harder than in many other classes of materials, I would say. I mean, sure, on a very long-term scale, then there might be something, but I don't see that happening within 5 or 10 years. That's my personal view on it. I would be happy to be wrong, but that's what I think.
So we have another question here. Kumar S asks if it's possible to get the electrochemical performance by providing electrolyte formulation and cell chemistries.
Electrochemical performance. Okay, so probably not exactly what you would mean by electrochemical performance, I'd say. I mean, what you can predict is, or what we can predict is, reduction and oxidation potential, for example. Where would the electrolyte break down? We would be able to predict transport properties and so on. But based on the simulation protocols in Compular Lab alone, we cannot predict, for example, the lifetime of the cell or something like that. So you would need another model, and in that model you could very well use the properties that we predict to sort of to feed that into that model. if that is what you mean by electrochemical performance. I might be wrong about that, but yeah.
Hi, I'm Kumar here.
Hi.
Hi. So, like you mentioned, another type of model can be used to get this information. May I know what is the model?
Yeah, I mean, for example, the models that are implemented in COMSOL, for example, or in
COMSOL.
Proteo, of course. So, I mean, different kinds of cell models that might also take into account cell aging and whatnot.
Fine. Thank you.
Well, I see Nilesh has raised his hand, so would you like to ask next?
Yes, thank you very much. Again, giving me the opportunity. I have a few quick questions. First, purely based on the how exactly you're operating your GUI. So it's only a web-based, or you are providing kind of a system-based licenses also? Because I can see most of the time we can operate directly from the base by doing login. But is there any possibility just we can separately install the app and we can work it?
I'm happy you asked that question, actually, because currently we only provide like the web-based solution where you would work against the cloud, so to say. But it's the top of the agenda in the development team for this the upcoming months to develop a version of it that we can that you could install on your own hardware. So in order to have something useful there, you would have to have access to fairly powerful compute, so probably some sort of HPC cluster or like very powerful computers. But if you have that, you should be able to then install that version of it. We don't have that as of now, but that's hopefully within a few months there will be something like that.
One more question I have. Thank you for the previous question. Second is, in your library, I have seen some of the ions and additives are available, but there are a long list of the ions. So I'm expecting that everything will not be available. So how exactly we can implement something new, ions or the chemistry? What inputs we require, or we can link with some external library kind of?
Right. Yes, so it depends a little bit on what the new thing you need is, so to say. So, and it also depends a little bit on what kinds of simulations you want to run. So if you want to run these MD simulations where you get transport properties, and if your compounds are not available in the tool, so then you can try to add them, and what you would need then is just a smile string, if you're familiar with smiles, like a description of the molecule. And if what you're adding is reasonably similar to what is already available in the app, there's a good chance that you will actually be able to just run it, and there would be no problem with it, so to say. That happens quite often with the customers we have so far. If it is chemically very different from what we're having, then we cannot just run it out of the box, because then the force field is not able to handle it. So then we need to do parameterization, as Rasmus mentioned before, where we would need to, do higher order calculations to get parameters eventually for the force field such that we could run it. If you want to compute redox potentials, on the other hand, that is something that we do with density functional theory, and that is sort of more general. It doesn't require parameters in the same way, so there is a very good chance that it will work out of the box regardless of what kind of molecule that you come with.
Okay. Perfect. I think I got the answer. And do we have any kind of comparison of your study with any kind of experimental result, which gives more confidence that, okay, we are that much of error difference, or we are just have exact match?
Yes, we do have a bunch of white papers primarily that we have released lately. We should have added some links to those, perhaps. They're all available on compulartech.com.
Okay.
I would suggest that you have a look there, and if you don't find what you're looking for, then get in touch with us, because we're constantly evaluating the simulations we're doing and so on to make sure it matches experiment and so on. So just get in touch with us.
Thank you very much.
Thank you.
We will get in touch.
Great.
Yeah, so our 2 minutes over time, but I would with this I would like to thank Eli and also Rasmus and Magnus for the presentation.